So hello and welcome students to another new video of Newton Gate, where we make your dreams come true. So this is a continuation of the previous video about the second chapter of the class 11, that is about the units and measurement, right? So as I had promised you in the previous video that I will discuss next 3 points, that is about the significant figure, the rounding off, and also the errors, types of errors in the next video. So I am here with that video only. Okay, so without wasting any time, let's start. Let us take few examples. So here in the first example it is given like 8, 4, 6. So can you say how many significant figures are here? Nothing to think about, it is 3. Here it will be 3. Okay, in the second example it will be 4, right? In the third we find a 0 is here in between two numbers, so this 0 is taken to be significant. So it is 3 zeros between two non-zero figure digits. So this will be 1, 2, 3, 4, and we will not take this trailing 0. So it will be only 1. Now come to the second set of examples. So here also there is a decimal point here. Can you see it? So whenever a decimal point is involved, then the trailing zeros are included within the significant figures. Here it will be 1, 2, 3, right? Here it will be leading zeros will not take, so it is 2. Here it is 3. Here it is 5. So even if there is a decimal point involved, we will not take leading zeros until and unless there is a non-zero digit here. So the example goes like that: in successive measurements, the readings of the period of oscillation of a simple pendulum were found to be 2.63, 2.56, 2.42, 2.71 and 2.80 seconds respectively in an experiment. So what will be the mean period of oscillation? What will be its mean value? Arithmetic mean, that is the true value. The sum of those 5 quantities, 5 digits or 5 readings divided by 5, the total number. We get by this summation we get the 13.12 that divided by 5, that is equals to 2.624 seconds, and we get rounded off to, we get 2.62. So we find that we round off to 2 decimal places. Why we round off to 2 decimal places? Because see here in the readings, all the readings are given in the significant, the number of least significant figure is 3. So I have to keep 3 significant figures here on. Now the absolute error, that is delta T1, T2, T3, T4, T5, that would be this T bar. The T bar is this thing, the arithmetic value minus the measured quantity, the difference of the arithmetic mean value and the measured value, that is 2.62 minus 2.63, 2.62 minus 2.63, we get minus 0.01. Hence I said you that absolute error can be in negative also, it can be plus or minus both. Okay, next is delta T2, that is T bar minus T2, we get 0.06. Delta T3, that is T bar minus T3, we get 0.020 seconds. Next is delta T4 minus 0.09 seconds. Delta T5 we get minus 0.18 seconds. Now the mean, we take the mean of the absolute errors. We don't take the signs here, so it will be just summation of the magnitudes of the absolute errors, that is 0.01, 0.06, 0.20, 0.09 and 0.18. The sum of these 5 divided by 5, we get 0.54, divided by 5, we get 0.01, 0.108. Now we round off, again we round off to 2 decimal places. Next calculation is relative error, that is equals to the delta T bar divided by T bar. The delta T bar is 0.01, we have already found it out, and t bar was 2.62, the arithmetic mean. So 0.11 divided 0.11 divided by 2.62, we get 0.04198, and we again round it off to 2 decimal places, we get 0.04. Okay, so next is the percentage error. Percentage error, we just multiply the 100 with the relative error. So 0.04 multiplied by 100, that gives 4%. Now when we write the error in terms of the absolute error, we try to write the time period t. We get that t is equals to 2.62 plus minus 0.11 seconds, and in terms of percentage error, it is t is equals to 2.62 plus minus 4% seconds. Okay. So next example, we take the time period of the simple pendulum, that is the t is equals to, we know the formula, and we can take it as 2 pi L to the power half multiplied by g, that is the acceleration due to gravity, to the power raised to the power of minus half. Okay, so while calculating the error, we will not take into account the 2 pi, that is the constant term. Okay, so given here the percentage error of L is plus minus 1% and percentage error of g is given as plus minus 2%. So the weighted fractional error would be delta x by x plus is equals to plus minus in bracket, that would be n multiplied by delta a by a plus m multiplied by delta b by b. Okay, now taking the same thing here it is x in the general formula, and in our case, in our problem, it is t. So delta t by t multiplied by 100, we will take the percentage error plus minus n. Here n is half, right? N is half, so that would be the half multiplied by delta L by L plus half multiplied by delta G by G into 100. Now the delta L by L, the percentage error is given like 1%. So it is the 1% and 2%, and there are the powers half and half. So half multiplied by 1% plus minus half multiplied by 2%, we get the percentage error in t, that is the time period, we get it as plus minus 1.5%. Okay. So here are the rules of rounding off. I have not wasted much more time in writing the rules. All the rules, you can get the statements everywhere in the book, or you can get it anywhere. So I have tried to give some examples. First example is x is equals to 7.82, and if the digit to be dropped is less than 5, then the preceding digit would remain unchanged. So it is 7.8. In the second example, take for 6.67. Now the digit to be dropped is greater than 7. So the preceding digit, the previous or preceding digit will raise to 1. So it is 6.7. From 6.6 it becomes 6.7. Next example, if x is equals to 16.351. Okay, if it is 16.351, if the digit is 5, not less than 5, if it is less than 5, then this law. If it is greater than 5, then this rule. If it is 5, we have to see another thing, that is the digit after that is 0 or non-zero. If it is non-zero, then we would increase the preceding digit by 1. So it becomes 16.4. Okay. In the fourth example, see, it is 5, but the digit after it is 0. Now we have to see the preceding digit also, it is even or odd. If it is even, it is kept as like. And in the last example, the example number 5, x is equals to 3.750. The digit after 5 is 0, so you would require to see the previous term. The previous term is 7, that is the odd number, and we will increase by 1, so that will lead to 3.8. From 3.7 it becomes 3.8. So these are the rules of rounding off. Okay. So find out those significant number of significant digits here. This is your question. You need to solve this one. So note it down in your copy and solve it now. So the video ends here. Thank you so much for watching the video.